right? Where we had seen that there is a string, and on that string loops like this were generated. Do you remember? In one case there were 3 loops. Do you remember this or not? Okay, and the string was vibrating, right? Okay, it was very fast, so we couldn't even see the string properly, wasn't it? Then in slow motion we were able to see it, right? Okay, so like this there can be 3 loops, for example, right? So once again let me point out this fact that we can do this only in those cases when L becomes equal to n lambda by 2, where n is an integer. Okay, this is clear or not, everyone? Why so? There can be 1 loop, or there can be 3 loops, or 2 loops, anything, integer number of loops. Do you understand what I am saying? If there is only 1 loop, L will be equal to lambda by 2. If there are 2 loops, L will be equal to 2 lambda by 2. If there are 3 loops, then it will be 3 lambda by 2. Okay, I hope this is clear, right? Now, continuing with the points. Number 4. Any 2 points between consecutive nodes. Any 2 points between consecutive nodes oscillate in same phase. Any 2 points between consecutive nodes oscillate in same phase. What I mean to say is, suppose there is 1 point here, let's say P, and there is 1 point here Q. So even though they have a distance between them, but their phase will be same. That's what I am saying. I know it doesn't go by what we have learned earlier. Do you remember this? It doesn't go by this, correct or not? This formula doesn't seem to work or agree with this sentence. Okay, did you understand what I said here? It doesn't agree with this. Now, why are these in same phase? Let's go through it again. It's that, listen to this carefully. The equations for a standing wave are not like traveling wave. Try to recall what we got. We got something like this, okay, where this bracketed part is amplitude. So we wrote it as A dash cos omega t, right? Okay, so what will happen is, if you take one particle and second particle, let's say P and Q, the only difference between them is this. Do you understand? The only difference between them is the value of A dash. But because at any time both are going to be on the positive side, it's like both go up then both go down together, right? So when 2 things are moving together, that would mean their phases are same. Also you can see it with a bit of maths. You can do it like this. This will be the equation for yp. Similarly, equation for yq will be as follows. You see, both are going to be same, positive, same sign, positive. Both are going to be positive, suppose. So then the only difference between these 2 equations is the number. It could be something like, let's say 5 cos omega t, and this could be something like, let's say 3 cos omega t. then what is the phase difference? This is called phase. I hope you remember. So what's the phase difference? Have a look at these two. What's the phase difference? It's 0. Understood? Phase difference 0 is clear because both angles are omega t. Right? So phase difference is 0. So that's the point number 4. Now let's go to a related point. Number 5. For points on two sides or for points with one node between them, phase difference of oscillations is 180 degree or pi. Okay. So we have written here that if you take any 2 points, with one node in between them, okay, take any 2 points, but there should be one node between them, only one node, not more than one node, right? So for example, I take the point the point Q and the point R, let's say. Focus on point Q and R. So for Q, we have already written that it will be something like, let's say, 3 cos omega. Okay, for example. But now for R, we are seeing that when Q is on the positive side, when Q is upwards, R will be downwards. Is that clear? When Q is above mean position, R will be below mean position. I hope that is clear based on whatever we have discussed or whatever we have seen in videos and animations so far. Right? Okay? So, do you realize that for some point R over here, the amplitude will be negative, because what that means is when Q part goes up, the R part is going down. So, this would mean it's something like, let's say, minus 4 cos omega t. Okay, let's say it's something like minus 4 cos omega t. Right? Again, 4 is just a number that I am giving randomly, okay, so that you feel comfortable with things. Now, how is the phase difference pi or 180 here? Is it not 0 again? Well, the answer is no. The reason is there is a minus sign here. So if I use a little bit of trigonometry, this will be written in this manner. Did you understand? Because of this property, cos of theta plus pi is equal to minus cos theta. Okay or not okay? Using that property, we can have that kind of equation, right? Now what this means is, now if you compare the angles, see, amplitudes are both positive now, that's how it is supposed to be. So now compare this angle, not with this angle, right? What's the phase difference? Have a look. The phase difference is pi. Absolutely clear? The sentence number 5. Absolutely clear? Okay. Right? So, any 2 points between two consecutive nodes, like P and Q, they are in same phase. But any 2 points, Q and R, with one node between them, remember only one node, not more than one. With one node between them, will have opposite directions for motion. That's why the phase difference is 180 degree or pi. Okay, these are some very small things that can be useful in some questions. Alright, now to answer Ankita's question, right, that she had at the start. Why is energy not distributed equally? Why is energy not distributed equally, or how can we say that energy is not distributed equally? For that we will have to consider the idea from SHM. Okay, so point number 6. Point number 6. Energy of oscillation at nodes is 0, okay, but maximum at antinodes. Why is it like this? Simple reason. Energy of oscillation from chapter SHM, everyone. Do you remember we derived in SHM E is equal to Do you remember we derived E is equal to in SHM? Because ultimately all the particles here, all of them are doing SHM. Isn't it? Right? All of them are doing SHM. Very good. Jai, correct. Yes, Amrita, that's the answer to your question in fact. It is half A squared. Do you remember that, everyone? Half A squared. Right? From chapter SHM we derived that K plus U will be half A squared. It will be a constant, it will not depend on anything. Right? Now, this is where it comes into the picture, brings amplitude into the picture. Why? Let's have a look. So do you realize that the points which are nodes, this one here, they have zero amplitude? Yes or no? The points that are nodes have zero amplitude, so then energy of oscillation is 0. Clear or not clear? Okay? But at antinodes, think about it. What is there at antinodes? The amplitude is at antinodes. The amplitude of oscillation is what? At antinodes, the amplitude of oscillation is maximum. Yes, 2A, maximum, right? It's the maximum amplitude possible. That's why energy is also maximum at antinodes. Is this clear? Energy is also maximum at antinodes. But that's not it. What this means is, have a look here, everyone. Let's say I am drawing a simple case. Okay, it is equally applicable even in case of more loops. Okay, I am just drawing one right now. So let's say the string is vibrating or oscillating like this. Alright? So if we will look for different points, this is of course a node and this is a node, they don't have any energy of oscillation, no problem. But here in the middle, right, at the midpoint of these two nodes, we are going to have the antinode. So that antinode is vibrating maximum. You get what I am saying? That antinode is vibrating maximum. Yes, I know me. That's why I'm waiting actually. Okay, now is the video clear? Okay, so here the amplitude is maximum, but if you go slightly to the right side, let's say there is a point P here oscillating like this, then there is a point Q here oscillating like this, then there is a point R oscillating like this, then there is a point S oscillating like this. So do you realize that as you go towards the node, the energy of oscillation will also decrease? Yes or no? As you go towards the node from the antinode, so energy of oscillation will also decrease. Okay, Ankita, everything clear now? The same thing of course will happen on this side as well, right? Okay, fine. Now, let's go to the next point. Okay, actually, I think we have written enough points here. Okay, we have written enough points here. Then I just suggest that you leave maybe 5 lines or something in case I think later that we need to write some point, we will write it. Okay, all right. Just leave a few lines. Okay, now let's go to the other point, the next topic. Okay, it is related to standing waves, of course. It is related to standing waves. Resonant frequencies, also called natural frequencies of a string tied at both ends. Okay, resonant or natural frequencies of strings tied at both ends. Right. So now we are going to talk specifically about frequency. Right? Lots of diagrams in this topic. The more diagrams you draw, the less you'll have to memorize. Okay, it will become natural if you draw more diagrams. Let's start. So the first possibility is, okay, case 1, L equal to 1 lambda by 2. See, we have noted that resonance can occur and standing waves will occur only in those cases where L is equal to n lambda by 2. So I am starting with L equal to 1 lambda by 2. So this would mean the diagram for this case would look like this. The one that I have just drawn. Have a look again. This kind of loop that you can see is equal to 1 lambda by 2. I hope you understood this. Clear or not clear? Clear or not clear? Okay. Now I'll just take one moment before we proceed to explain how we get resonance here. What's really going on? It's that suppose at this point you would have put a vibrator instead of fixing it. Let's say you would have put a vibrator. Then listen to this carefully. What would happen is a traveling wave will be generated, let's say, and it goes towards this side. At this fixed point, it will hit, it will get reflected, and you know when it is reflected, it becomes inverted. Yes or no? From a fixed point, if it's reflected, it will become inverted and then travel like this. Then once again, when it will hit here, it will get reflected and inverted. So what this means is that after two reflections and two inversions, it will come back like this. But that will take how much time? If this distance is lambda by 2, going there and coming back means traveling distance lambda. Yes or no? Yes or no? Going there, coming back. How much distance traveled? Lambda. Clear or not clear? Why so? Lambda by 2 right side and then coming back. Lambda by 2 left side. So for traveling this much distance, do you realize that it takes a time period capital T? Why? Because speed formula. Speed is equal to distance upon time. Okay, simple idea for constant speed. Speed is equal to distance traveled upon time. So how much time is this? Lambda by v, or you can alternatively put v equal to lambda f here. So you get lambda cancelled and t is equal to 1 by f. That is nothing but time period. Yes or no? Did you understand the maths here? Okay. I repeat, lambda cancelled. So t is equal to 1 by f, but 1 by f is called time period. right? Okay, what does this mean? This is just like swinging a child on a swing. Listen to this carefully. What would you do when you are trying to make a child swing with more amplitude? You push here, then you wait for how much time? For one time period, isn't it? The child will go there and come back. So time period t, correct? And then you push again. Yes or no? Yes or no? Do you remember this thing about resonance? Okay, well, same thing happened here. Have a look. Have a look. First wave pulse that was generated, when there came back, now it's ready to go back after reflection. I repeat. First wave pulse, when there came back, now after one time period, it is ready to go back, correct? So it will try to go over there. And when it tries to go over there, the source here, source will also complete one oscillation in time period t, correct? So after time t, once again it's like the source will push the string. Just like you push the string, the source will push the string. So now on this string there are going to be two waves. Why two waves? One is the twice reflected wave. You understand what I am saying? One is the twice reflected wave. Which one? When there came back, now it's going back. Correct? And the second is the second wave generated by source. Second is the second wave generated by source. So now these two waves will add with each other. These two waves will add with each other. Fine. What will happen then? Both these waves will go there, come back, and now they are ready to go back again. At that time, source after one time period will generate a third wave. So the next time there will be three waves. Did you understand? Did you understand or not? Okay? Because the earlier two waves went there, came back, and now they are ready to go again towards that right side. And at the same time, the source is also oscillating, so it's sending one more wave towards the right side. So like this, all the three waves will get superposed. Okay, they will have superposition. So will this process ever stop? Ideally, no. So ideally what will happen? Amplitude will become infinite. Why amplitude will become infinite? Because the fourth time there will be four waves. The fifth time five added on to each other. So if first time it was like this, second time two such waves are added. So by superposition principle you have larger. Third time one more wave is added. So even larger. Fourth time even larger. Fifth time even larger. Do you realize string will break? Do you realize that the string will break? Yes or no? Why will it break? Because amplitude will keep increasing. Do you remember what I told you about resonance, everyone? Do you remember what I told you about resonance? That in resonance amplitude will keep increasing, it will become infinite. Right? But there is a problematic factor. In reality, there is something called damping. In reality, there is something called damping. So, will the amplitude always keep increasing like this? No. But yes, it will remain some fixed large value. That is what we were seeing in all these videos. Right? That when the string oscillates, it oscillates with a large amplitude. Okay, it oscillates with a large amplitude but not infinite. Right? Why not infinite? Because there is always going to be damping. So this is basically resonance going on here. Right? Wave goes there, comes back. When the next time it tries to go, source adds its own new wave on it. So superposition principle, now you have two waves added, so more amplitude. Third time even more amplitude, fourth even more. Like that the waves keep adding, but because of damping they get a constant amplitude. So that is what is standing waves, right? This is how standing waves are generated. Again, they don't go away. Let me tell you that. If there was no damping, and you would vibrate it once, it will just keep doing that again and again and again for infinity. It would never stop. Right? Okay, anyways, so we will continue with this point the next time. Okay, so I have explained why resonance is giving standing waves. Okay, right, then we'll derive all these cases the next time. Okay, goodbye everyone.